Hello Calculus, these are the video notes for our lesson on function curve sketching using the first and second derivative. So as we go through these notes, we're going to talk about the shape of a function based on its derivative, and we're going to introduce a few more nuanced vocabulary terms. So let's start out. In this first video, we're going to focus on the first derivative test. From Corollary 3 of the mean value theorem, we know that the derivative of a function is positive. If the derivative is positive, then the function is increasing, and if the derivative is negative, the function is decreasing. So our first derivative test, we're going to use the knowledge that a function has a maximum if the derivative changes from positive to negative, and a minimum if the derivative changes from negative to positive. So looking at this example, you can see that there are two maximums. One where the derivative is undefined and one where the derivative is 0. There's one minimum where the function was the derivative was negative and then the derivative was positive. And then there's one critical value where the derivative was positive and then the derivative was positive again, making it neither a minimum nor a maximum. Using the first derivative test, we're going to do two algebraic examples, and this is the first one. So to do the first derivative test, you first have to identify where your critical values are located. So we're going to find the derivative of this polynomial function. And we're going to set it equal to 0. Because all of these terms have a factor of 3, I can divide everything in the equation by 3, including the 0. And then I'm going to factor this quadratic by looking for numbers that multiply to be -3 and can add to be -2. This leaves me with two potential critical values, one at +3 and one at -1. So we're going to call this maybe C1, and we'll call this maybe C2. From here, we're going to move on to a sign chart, which is going to allow us to determine if this derivative is positive or negative on either side of each of these critical values. So over here on the side, we're going to create our sign chart, and we're going to focus on our critical values. I'm going to go ahead and put them in numerical order as they would appear on a graph. We're going to choose an x value to the left, in between, and to the right of each critical value, testing whether the derivative is positive or negative. So for this first one, and remember our derivative is x squared is f prime x equals, and I'm going to go with the original version, but I'm going to factor it because it's going to make it easier to plug in values. So I'm going to take out that 3, and then I know the two factors were x minus 3 and x plus 1. So here I am with my derivative, and I'm going to plug in our first critical value, which is -2. If I put a -2 here and a -2 here, then I'm getting a +3 times a -5 times a -1. And that's going to give me an overall positive result. Then I go to check the number 0. And so I'm going to plug in a 0 here and here. And that's going to give me a +3 times a -3 times, oh my goodness, times a +1, which is going to give me an overall negative result. Finally, I'm going to plug in my third value, which is 4, and I'm kind of out of room, so let's imagine a 4 here. Then I get a +3 times a positive times another positive, and this is going to give us an overall positive result. So as we can see, the derivative goes from positive to negative, which means the function is going from increasing to decreasing, and this tells us that we have a max at -1. On the other end, we have our derivative going from negative to positive, which means our function goes from decreasing to increasing and gives us a minimum at 3. And so our solution is that C1, which was 3, is a minimum, and C2 is max. And remember, location is just the x-coordinate. So if I'm asking you for the location of the extrema, I'm just asking you for the x-coordinate of the extrema. Second example is a little more complex algebraically, but we're going to follow the exact same process. So step 1, we're going to identify the derivative as 5 times 1/3 x to the negative 2/3 minus 5/3 x to the positive 2/3. Simplifying this down, I'm going to keep the 5 in the numerator, the 3 in the denominator, and the x to the negative 2/3 is going to become a positive factor of the denominator. Then I've got 5 with an x to the 2/3 in the numerator over 3. So here's my derivative. I need to set this expression equal to 0 and solve for my x. Now right away, with a rational function, there are domain restrictions, and we know that the critical values also exist where the derivative does not exist. So the first critical value, so it's this, or the derivative does not exist. So right away, I have a denominator, and I know that x cannot equal 0. So my very first critical value is 0 because the derivative does not exist at 0. Now I'm going to solve this equation and see if I can find any other critical values. With rational equations, you want to multiply by the common denominator, which in this case is 3x to the 2/3. So I'm going to get 0 equals 5, because if we multiply this term by 3x to the 2/3, it's going to cancel. And if we multiply this one, it's not going to cancel. We're going to do a little arithmetic here. So let's switch. Minus, the 3's will cancel. But I'm going to get 5x, and I'm going to add these exponents using the product rule. So I get 5x to the 4/3. From here, we're going to subtract the 5, or add the 5x to the 4/3 to the other side. We're going to divide by 1. Nope, we're going to divide by 5, which gives us that the expression is equal to 1. And then we want to be really careful here. I'm actually going to break down this exponent in 2 steps. So the first thing I'm going to do is raise both sides to the 3rd power. Here and here. And that's going to give me the equation 5x, not 5x, x to the 4th equals 1. And so I'm going to 4th root both sides. And just like with a square root, when you take a 4th root, you get positive or negative 1. So now I have narrowed down my critical values to negative 1, positive 1, and 0. Creating my sign chart. Negative 1 is the smallest, then 0, then positive 1. And so to find the value of the local extrema, keep in mind we've already found the location. I was just rereading the directions again. Find the location, we did. Negative 1, 0, and 1, except there's a chance that these aren't actually extrema, that they're just critical values. So let's put in our x, f prime of x, and then we need to plug in each of these into our function derivative, which I'm going to highlight in green over here. And this is where we're going to substitute. Now I'm going to be using a calculator for this one instead of my mind because I want to make sure that I'm accurate. So let's pick something to the left of negative 1, in between negative 1 and 0, in between 0 and 1, and then after 1, which is 2. So I'm going to plug in each of these to my function. And I'm actually going to use a shortcut with my calculator where I type this equation into this derivative into my y equals as if I was going to graph it. And then I use the table to find each of the evaluated terms all at once. So then I'll go to table set, and I'll change the table to count by 0.5 so that I can also see these decimal values. So table set, I'm going to start the table at -2, and I'm going to change the table to count by 0.5s. So I'm getting at -2 that the derivative is negative. At -0.5, the derivative is positive. At 0.5, the derivative is positive. And then at 2, the derivative is negative. That means that 0 is not a local extrema. We have a decreasing to increasing minimum at -1 and an increasing to decreasing maximum at +1. And so this is how we use the first derivative test to locate our local extrema.